Welcome everyone. In this video, I will be covering the concept for section 15.7, the triple integrals in cylindrical coordinates. Earlier, we saw polar coordinates and how they can be used in evaluating certain double integrals in an easy way. Same way, cylindrical coordinates are going to be helpful in evaluating certain triple integrals which are otherwise very hard in the Cartesian way. So what are cylindrical coordinates? In the cylindrical coordinate system, the point P in three-dimensional space is represented by an ordered triple or theta z, where r and theta are polar coordinates of the projection of P onto the xy plane, and z is the directed distance from the xy plane to the point P. So it is very clear from this picture. P is the point, and the projection of it is, let's say, P prime onto the xy plane. And then if you take the polar coordinates, the projection of the point P1, and if you take OP1, OP prime to the x-axis, that angle is theta, the distance of O to P prime is R. So it is the regular polar coordinates of um, the point P prime. So P prime is a projection of the point P onto the xy plane. Now Z is the perpendicular distance from P to P prime. So to convert from cylindrical to rectangular coordinates, we use the equation x equal to r cosine theta, y equal to r sine theta, and z equal to z. Whereas to convert from rectangular to cylindrical, we use r square equal to x square plus y square, tan theta equal to y over x, z equal to z. We'll see one problem here, problem number 3, part B. Change from rectangular to cylindrical coordinates. From rectangular to cylindrical coordinates. So what is given is in the problem x, y, z. We are going to change to r theta z. So let's use the relation. So we are going to use the second equation. So r square equal to x square plus y square. So r square equal to negative 2 square plus 2 radical 3 the whole square. So which would be 4 plus 4 times 3. So that will be 16. So r square is 16, r equal to 4. Then we got r, which is one of the coordinates, one of the cylindrical coordinates. Then we need to find out theta. So let's find out tan theta first, which is y over x. Y equal to 2 radical 3, x is negative 2. So it is negative radical 3. So when you, so you have to look for an angle theta whose tan is equal to negative root of 3. But we notice that the point xy, so negative 2 comma 2 root of 3 lies in the second quadrant. So we are going to pick an angle theta in the second quadrant whose tan is negative radical 3. So which will be pi minus pi by 3, because the reference angle is pi by 3. So it has to be lie in the second quadrant. So it will be equal to 2 pi by 3. So we find that r equal to 4 and theta equal to 2 pi by 3. And we know that by definition, z is equal to z. So we have z coordinate is z of xyz, which is equal to 3. So the cylindrical coordinates corresponding to negative 2, 2, radical 3, 3 are r theta z, which are r equal to 4, theta equal to 2 pi by 3, and z equal to 3. So it is important to note whenever you find theta, it is important to note that which quadrant the point x comma y lies. Then that determines the angle, the appropriate angle theta. How do you change from rectangular coordinates to cylindrical coordinates in a triple integral? The idea of introducing this cylindrical coordinates is how we can simplify certain or evaluate certain triple integral problems in an easy way. Triple integral over E f of xyz dv is equal to integral alpha to beta, which are the angles for theta, then integral h1 of theta to h2 of theta, which are the bounds for r, and the bounds for z would be u1 of x comma y, which is r cosine theta, r sine theta, u2 of r cosine theta, r sine theta, of f of x, y, z. X is r cosine theta, y is r sine theta, z is z. Then this dv will become, this dv here would become r dz dr d theta. dv changes to r dz dr d theta in polar coordinates. Here, what is the solid region E? E is r theta E, r theta z. Theta lies between alpha to beta. Theta lies between alpha and beta. R lies between h1 of theta to h2 of theta. Then z lies between u1 of xy to u2 of xy, where x and y in cylindrical are r cosine theta or sine theta respectively. Thus, we replace x by r cosine theta, y by r sine theta, and dv by r dz dr d theta, and use appropriate limits of integration. Note, cylindrical coordinates are useful in problems that involve symmetry about an axis, and the z-axis is chosen to coincide with the axis of symmetry. For instance, the axis of the circular cylinder with Cartesian equation x square plus y square equal to c square. So this is an equation of a cylinder because there is a missing variable. Whenever there is a missing variable, then the axis of the cylinder will be directed towards the missing variable axis. In this case, the z-axis. So is the z-axis. In cylindrical coordinates, this cylinder has a very simple equation, r equal to c, because x square plus y square equal to c square will mean r square equal to c square. So it has a simple equation in cylindrical coordinate. coordinates, the cylinder can be represented as r equal to c. This is the reason for the name cylindrical coordinates. So if you look at the cylinder that is shown in this diagram, then this is the point on the y-axis, and it's of radius c. X square plus y square equal to c square is what's shown in this picture, so, which is r equal to c in cylindrical coordinates. So the point on the y-axis will have coordinates 0, c, 0. The point on the x-axis will have coordinates c, 0, 0. And it is r equal to c represents um, a cylinder. It is x square plus y square equal to c square in Cartesian. There are some problems that are done in the videos for the section. Please refer to them in the section videos. Problem number 17, problem number 22, and problem number 23. All these are done using cylindrical coordinates. Please check those videos, check those problems in the videos for the section. Refer to the videos for section 15.7. Hope this video helps.